See here, this is the mid-type cycloconverter. This is the bridge-type cycloconverter. Both circuits can be used for step-up cycloconverter. See here in the waveform. In the waveform, this is the step-up cycloconverter. Why this waveform is called step-up cycloconverter? Anyone? Anyone can answer? Why this waveform is called step-up cycloconverter? From this waveform, how we can say this waveform belongs to step-up cycloconverter? Can anyone explain? Regarding time period and frequency. See here, for input is this one. Input is this one. One positive cycle and negative cycle combination is nothing but one cycle. For one cycle time period, input time period is Ts. But output time period you see, plus positive cycle and negative cycle. Take only one cycle. How many similar cycles are there in one cycle of input? 1, 2, 3, 4, 5, 6 cycles are there. That means if you take one cycle, time period is reduced by 6 times. That means frequency is increasing by 6 times. That's why this is called step-up cycloconverter. That's why it is called step-up cycloconverter. Now we'll go for step-down cycloconverter. This is the waveform for the step-down cycloconverter. Same circuits, these two circuits can be explained for step-down cycloconverter. Circuits will be same, both for step-up cycloconverter and step-down cycloconverter, but the waveform is different. Operation is different. Okay, now we'll see step-down. Here in the step-up cycloconverter, we are using forced commutation. Forcibly we are switching off and we are giving firing pulse to N2. Similarly, if we are forcibly switching off N2 and we are giving from 0 to pi, this is the positive cycle input. Alternatively, we are giving firing pulse to P1 and N2 because in positive cycle P1 and N2 will be forward biased. From pi to 2 pi of this polarity will change. Now N1 and P2 will be in forward biased. Now in negative cycle we will give alternatively for P2 and N1 firing pulses. Like that you are using forced commutation in this. But in step down cycloconverter, we will use natural commutation. We will use the natural commutation. What do you mean by natural commutation? Natural commutation means by itself it will turn off the SCR. SCR will be turned off by itself when the voltage crosses. See, this is the input voltage. Let us take. This is one cycle. This is the second cycle. This is third cycle like this. One positive negative is one cycle. Here one positive negative is one cycle. One positive negative is one cycle. This is the input and this is the output. So input is this one. They are drawing reflection here. See, this reflection is only for reference purpose. Actual waveform is this one. Actual waveform is input voltage is this thick line. For drawing the output voltage conveniently, they are drawing one reflection for this main waveform, for this input waveform. They are taking one reflection here. Now see here, during positive cycle, what I had to, during positive cycle, this will be plus and this will be minus. This will be plus and this will be minus. Now which thyristors are in forward bias during positive cycle? Can anyone say in this? Positive cycle event thyristors?
P1 and N2, sir.
P1 and N2. See here, P1 and N2. Negative cycle P2 and N1. Now I am concentrating only on P1 and N2 during positive cycle. During negative cycle, it will go for P2 and N1. Now what I am doing in positive cycle, if P1 and N2 are forward biased, I am not giving firing pulse to N2. I am giving firing pulse only to P1. In step down cycloconverter, you see the waveform. See, during the entire positive cycle, I am giving firing pulse only to P1 only. Now come to negative cycle of the input. So at 0, this is pi. At 180 degrees, automatically P1 will be off. P1 will be off. Why? It is coming into negative cycle. In negative cycle, you see, in negative cycle, which thyristors are in forward bias? P2 and N1. Now I am giving only firing pulse to P2. Negative cycle, P2 forward. I am giving gate pulse because P2 and N1 are forward bias. So I am not giving firing pulse to N1. I am giving firing pulse only to P2. Suppose in positive cycle, if P1 is non-state, what is the current direction? This direction. When negative cycle, when P2 is given forward bias, current direction is same direction. Load low current direction change in the whether it is in the positive. If positive cycle P1 means from anode to cathode current will flow like this. Similarly, negative cycle P2 N1, but we are giving firing pulse only to P2. Now current direction is not changed in the load. Current direction is not changed in the load. This negative cycle is also converted to positive cycle. This waveform is for RL load. That's why we are getting negative spike. Up to beta, up to extinction angle beta, we are getting the voltage. And we are giving firing pulse here, P2. From P2, this negative cycle is converted to positive cycle. Again go to positive cycle, which one forward bias? P1. And negative cycle P2. When you're giving firing pulse to P1, P2, P1, P2 like this, for continuous 2 cycles, we are giving firing pulse alternatively to P1 and P2, P1 and P2. Okay. Now, for 2 cycles, we are giving firing pulses to P1, P2. For next 2 cycles, here I am giving firing pulse N2, N1, N2, N1 for next 2 cycles. Again, next 2 cycles, P1, P2, P1, P2. Now, here, see negative cycles you are getting for next 2 cycles. For first 2 cycles, only positive pulses you are getting. For next 2 cycles, you are getting negative. Why means, see during positive cycle, P1 is given forward bias. Current direction is in this direction. When negative cycle, P2 is forward bias. Now current is flowing through P2 like this. Current direction, the load is in this direction when P1, P2 are on. P1 in positive cycle, P2 in negative cycle. Since polarity is not changed in the load, negative cycle is also converted to positive cycle. Here positive cycle remain as it is, negative cycle is converted to positive cycle. Now come to the next cycle, next positive cycle. In the next positive cycle, P1 and N2 are forward bias. But now for next 2 cycles, I am not giving firing pulse to P1. I am giving firing pulse to N2. If you give firing pulse to N2, current flows from anode to cathode. Now see in the load current direction is in this. Now positive cycle N2 I am giving forward bias. Now come to negative cycle, this polarity is changed. Now N1, P2 are forward bias. Now I am giving firing pulse only to N1. If you give firing pulse to N1, the current flows like this, N1 low. So when N2 is in forward bias in the positive cycle, current is in this direction. N1 forward bias in negative cycle, current is in the same direction. When P1, P2 we are giving, current is in this direction. When N1, N2 are forward bias, we are giving current is in this direction. That's why we are taking negative cycles. For N1 and N2, we will take negative cycles. See, when you give during positive cycle, N2 is forward biased, but current direction is reversed in the loop. That's why we are getting here negative. Again, during negative cycle, you are giving firing pulse to N1 only, not P2. Then current direction is same as that of N2 in the load. So this one. For next cycle also N2, N1. So when you give firing pulse to N2, N1, current direction, the load is reversed. That's why you are drawing in the negative cycle. Now again P1, P2, P1, P2. Next again N2, N1, N2, N1. Is it clear, the diagram? Now see, this is the input cycle. What is the time period of one cycle? One positive and negative. This is TS. Now see the output time period. Take the average of these 4 cycles. 1, 2, 3. All positive cycles take average. This is the average up to here for 2 cycles. Take average of these 4 cycles. This is the average. Now see here, time 1 cycle, 2 cycles, 3 cycles, 4 cycles. For 4 cycles, we are getting one sine in the output. This is the output. Now time period is increased by how many times? 4 times. Actually, input time period is only up to here. But see the average. This dotted line is the average. This is one positive cycle up to here. This is one negative cycle. Time period is increased by 4 times. This is the time period of 1 cycle. Now for 4 cycles, we are getting the average. Time period is increased by 4 times. If time period is increased by 4 times, what happens to frequency? What happens to frequency? Frequency reduces by 4 times. If you take average of this dotted curve, 4 cycles you are getting. Here 1 cycle time period is t. 4 cycles time period is 4t. Now frequency is reduced by 4 times. Okay, because frequency is inversely proportional to time period. That means frequency is reduced, output frequency is less than the input frequency. That's why I'm calling it as step down cycloconverter. Step down cycle. Since it is the RL load, we are taking the load as RL. Immediately the current, if you give firing pulse to P1 here, immediately current is not rising. Up to pi, it will increase. Then when P1 is off, slowly the current will decrease to 0. This is beta. The point where current extinguishes to 0 is nothing but beta. Now we are giving firing pulse to P2 here. Now negative cycle is converted to positive cycle. So any doubt in this? If you are having doubt, you can ask me. Once if you get the doubts only, then only the waveform will be clear. You can ask the doubts in this waveform. Anyone? Here there is no necessity of forced commutation, natural commutation, because after pi, current is reverse bias. That's why current will decrease in the load to 0. You can ask me the doubts. This is for mid-tap cycloconverter. If you take bridge type, what you will get? Initially P1, P2, next P3, P4. See here, if you take bridge type, here you will get P1, P2. Here you will get P3, P4. P1, P2, P3, P4. Here N1, N2, N3, N4. N1, N2, N3, N4. If you take bridge type, at a time 2 thyristors will be on. P1, P2, P3, P4, P1, P2, P3, P4. N1, N2, N3, N4. N1, N2, N3, N4. Like this. Any doubt? Doubt into it again.